Chapter 12 in the Abstract Algebra series is on congruence. And problem number 1 says, using set builder notation, specify the elements in the modulo 20 congruence class 7. Well, the modulo 20 congruence class 7 consists of integers congruent to 7 modulo 20. In other words, these would be integers that differ from a multiple of 20 by 7. So you could write it in set notation as 20 times k plus 7, where k is an integer. And if you want to be more specific, you could multiply k by 0. That would give you 7. And once you establish that integer, then you can just add and subtract 7 to keep building the set. Number 2, solve for x in this modulo 7 equation. So we have the class 3 plus x would equal the class negative 1. And fortunately, when we do modular arithmetic, the way to go about solving these is not really counterintuitive at all. So to get x by itself, I just subtracted the 3 class from both sides. And then there's a rule that says that if you have class A and you want to add to that class B, then that would be the class A plus B. And it works the same way for subtraction. So once I subtract class 3 from both sides, I can combine those two into class negative 4. And since we like to write classes using the smallest positive integer, I just add 7, negative 4 to get 3. Why did I choose to add 7? Because we're in modulo 7. Number 3, solve for x in this modulo 5 equation. Same concept. We're going to use the switching sides rule, which means that I can subtract the 3 class from both sides. And then once I do that, I can combine all of those within one class, which gives me class 4. Number 4. Determine the elements of Z4 that have a multiplicative inverse. Z4 can be thought of as the set of integers that you could possibly get as remainder values if you divide any integer by 4. If you divide any integer by 4, the possible remainders will be 0, 1, 2, or 3. And since we are looking for a multiplicative inverse, we know that the operation is multiplication, and the identity element under multiplication is 1. So what elements have a multiplicative inverse in Z4? I chose to use a Cayley table. And as you can see, 1 times 1 is 1, which is the identity. And also 3 times 3 gives you 1, which is the identity element. So the inverse of 1 would be 1, and the inverse of 3 would be 3. So 1 and 3 both have multiplicative inverses. Number 5. Number 5 says, what is the additive inverse of the class 5 in the group of the modulo 8 congruence classes? And before we get started, let's fix a typo. This should actually be an 8 since we are in modulo 8. The classes in modulo 8 would be 0 through 7 on the integers, because if you divide any integer by 8, you're going to have a remainder of 0, 1, 2, 3, 4, 5, 6, or 7. So what is the additive inverse of the class 5? Well, if we go down to the class 5 under addition, notice that if we add class 3 to class 5, we get class 0, and 0 is the identity under addition. Likewise, we can also check that if we take class 3 and add it to class 5, we also get class 0. So 3 and 5 are additive inverses of each other. Number 6. Number 6 says to solve for x in 3x is equivalent to 33 mod 14. I started off using a method that I'm going to elaborate on a little more in problem number 7, and then I decided not to go that route. Since 3 and 14 are relatively prime, that means that I can use the cancellation rule, and that means that x would be 11, equivalent to 11 in mod 14. And again, we can do the cancellation rule because 3 and 14 are relatively prime. Number 7 is going to be quite different because 3 and 6 are not relatively prime, so we cannot use the cancellation rule. What I chose to do for this one, because I like my math to be visual, is I chose to put the modulo 6 set in a Cayley table here. And since we're in modulo 6, our row and column entries will be the integers 0 through 5. Notice that if I multiply 3 times 1, I get 3. Also, 3 times 3 gives me 3. And 3 times 5 gives me 3. And you may be thinking, well, am I not looking for 33 when I multiply 3 times another integer in modulo 6? The answer is yes and no, in a way. To fill out the Cayley table, I need to realize that 33 is equal to 3 in mod 6 because 6 goes into 33 5 times with 3 as the remainder. So yes, 33 is equivalent to 3 in mod 6. And we know that 3 is an element in our table here. So 3 times 3 gives me 3. 3 times 1 gives me 3. 3 times 5 also gives me 3. So we have 3 solutions here. 1, 3, and 5. Number 8. If 8 is equivalent to C mod n and B is equivalent to D mod n, are the following statements true? Would A plus B be equivalent to C plus D in mod n? And would A times B be equivalent to C times D in mod n? And the answer is yes, because if A is equal to C in mod n, then they are from the same class. In other words, they are the same. Same argument with B and D. If B is equal to D in mod n, then they're in the same class. That's the same class. And if you choose to add, let's say, B to one side, that would be equivalent to adding D to the other side. Likewise, if you choose to multiply one side by B, that would be equivalent to multiplying the other side by B, which is equal to D. Number 9. Determine 6 squared mod 7, and then use that to determine 6 to the power of 1,000 mod 7. Well, 6 squared is 36, and 36 mod 7 is actually 1, because 7 goes into 36 5 times, the remainder would be 1. And we can rewrite 6 to the power of 1,000 as 6 squared to the power of 500, because 2 times 500 is 1,000. And since 6 squared is the same as 1 in mod 7, I'm going to substitute 1 in place of the 6 squared, and 1 to the power of 500 is 1. So 6 to the power of 1,000 in mod 7 is just 1 mod 7. Number 10, show that if n divides m and a is equivalent to b mod m, then a is equivalent to b mod n. If n divides m, then we know that m has to be some multiple of n. I chose to write m is equal to k times n, where k is an element of the integers. We're also given that a is equivalent to b in mod m, which means that a minus b is some multiple of m, and I chose to use r, where r is an integer. So let's let a minus b equal to rm. Again, a minus b is just a multiple of m, and we know that m is equal to kn, and then using the associative property, we can see that a minus b is just a multiple of n, And if a minus b is a multiple of n, then a is equivalent to b mod n.